Maths Aspirants is a collective of mathematics students, research scholars, faculty members across India and abroad, initiated by myself in 2017. And we used to organize several online programs, online test series, online problem solving sessions, and webinars to help the students who are preparing for different national level competitive examinations in higher mathematics. As a part of the online problem solving session series, today we have Dr. Sayak Sen Gupta to handle a session on linear transformations. Dr. Sayak handled one problem solving session in linear algebra, basics of linear algebra in the last month. Today, he is with us to handle a session on linear transformations. As all of you know, linear algebra is one of the important topic in any competitive examination, especially IIT JAM or CSIR NET or GATE examination. There will be a lot of questions from linear algebra. So I am sure that today's sessions will be really beneficial to anyone who are seriously preparing for these type of competitive examinations. Let me introduce Dr. Sayak. Dr. Sayak is from West Bengal. He did his BSc from Ashutosh College under University of Calcutta and did his MSc from University of Calcutta and PhD from Binghamton University, USA. And his broad research area is number theory. So I'm very happy to introduce, and also I would like to express my sincere gratitude and thanks for Dr. Sayak for being with Math Aspirants group. I'm sure that today's session will be really helpful to all of you. I welcome everyone to this program. Welcome, Dr. Sayak.
Thank you. I would like to begin by thanking Dr. Vinod for inviting me. And so we will basically think of this as a continuation from the last session. I've introduced the basic topics that one needs to know in order to do problems. And this topic, linear transformation, was introduced last time, especially the basics about nullity of linear transformations and image of linear transformations. So we will just jump into problems. I will go through one or two basic things, which is basically just recalling what we did last time in a very, very brief manner. And then we can do the problems without any. So as I said, we will start with recalling what we did last time in a very, very brief manner. And that's basically all we need for all the problems that we will see today. Okay. So for example, we looked at the rank nullity theorem, which basically talks about the dimension of the space where the linear transformation is starting from. So if you have a linear transformation T from V to W, V and W being linear spaces over the same field, then the dimension of V must be equal to rank of T plus nullity of T, where rank of T is the dimension of the image of the linear transformation T, and nullity of T is the dimension of the kernel of the linear transformation T. And the injective linear transformations always take linearly independent sets to linearly independent sets. So this is one good way to check if a linear transformation is injective or not. You just look at you just find first the basis of the domain set, one basis of the domain set, and see if it doesn't really have to be basis. You can take any linearly independent set really, and see if it goes to a linearly independent subset of the codomain or not. And more or less same reasoning goes when you deal with isomorphism, where the basis always goes to a basis. And that is something which is kind of intuitive, that the dimension has to be preserved because the linear transformation, which are isomorphisms, are invariant that way. The dimensions are always the same if you have isomorphism between two vector spaces over the same field. So like last time, we will deal with all the vector spaces over R or C. And I will make it precise when the problem starts, that this is a vector space over R and this is a vector space over C whenever we need. Okay, so let's go to the first problem. Suppose you have a linear transformation from R2 to R3, where, of course, R2 is the Cartesian product of R with itself, and R3 is R with itself, Cartesian product 3 times. And I'm defining it in a matrix way, but you can also think of this as a row vector, x comma y, going to the vector x comma x plus y comma y. So our job is to write T as a matrix with respect to the standard basis of R2 and R3. So when I say standard basis, I actually mean the ordered standard basis of R2 and R3. So let me be precise about this. So a basis of R2 will be 1, 0 and 0, 1. And R3 would be 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, so we just have to keep track of where these 1, 0, and 0, 1 vectors are going in R3. So what is the image of 1, 0? What is T 1, comma 0? So in this case, x is equals to 1 and y is equals to 0. And you can see clearly that this is nothing but 1, comma 1, comma 0. And T of 0, 1 is equal to 0, 1, 1. So now we have to express this in terms of the basis vectors here. And that is quite easy, really. It's 1 times 1, 0, 0, and 1 times 0, 1, 0, and 0 times 0, 0, 1. Similarly, this one would be 0 times 1, 0, 0, 1 times 0, 1, 0, and 1 times 0, 0, 1. So now we have the scalars, and so we should be able to write the corresponding matrix corresponding to the linear transformation, I mean, and that is just writing the coefficient in the row way and then taking the transpose of that matrix. So it's going to be 1, 1, 0, and 0, 1, 1. So that is the matrix corresponding to the vector T, corresponding to the linear transformation T. Okay. So we did one problem like this last time, but we didn't really go into too many problems. So I would like to rectify that this time. So let's see another problem like that. Suppose you have an element tau from the symmetric group Sn. So what is a symmetric group? Symmetric group is basically the group of permutation on a set of n elements. In this case, the set of n elements is the set of natural numbers, the first n natural numbers, basically. So we are looking at all possible permutations of 1 through n, and we are picking one element at random from that group. By the way, when I say group, in this case, this is actually a group where the group operation is composition of functions, because these are permutation, these are ultimately bijective functions on this set of 1 through n. So this is really a group. Now we are considering to be Rn, and now we are defining a linear transformation phi of t in this format. Remember from last time we said that defining a linear transformation at the basis is enough because every element can be represented in terms of basis. So that's what we are doing here. This definition makes it unique. So what we are doing is we are basically looking at the index and we are sending it to tau of I. So meaning where is I being taken by tau. So that's what's going on. I should talk about what EI means, although some of you might already know it. EI is just the row vector or column vector. In this case, I'm writing it as a row vector. So row vector with all entries 0, except for the ith entry, which is 1. So this is the ith entry, and everything else is 0. So similarly, tau I is, let's say I is being taken by tau to j, then E of tau j is equals to E of j, which is going to be similarly defined. Okay, and you can clearly see that this is indeed a basis of Rn as a vector space over R. Of course, this n being arbitrary, this is not a very good problem. So I would like to make it precise by assigning some predetermined values of n and a corresponding element of the symmetric group. So let's see what happens with 1. For the first one, what's going on is, so let me write it here. E1 is being taken to E3 because you can see here that 1 is being taken to 3. 2 is invariant. It goes to the same element. Or maybe I shouldn't say invariant. In this case, I should say fixed point. And then E3 is going to E1. Okay, so that being said, the matrix is now clear. The matrix is going to be, so 0, 0, 1, because E3 is here. E3 is here in the first one. That means 0 times E1 plus 0 times E2 plus 1 times E3. That's why 0, 0, 1. And similarly, you can see that the other ones are 0, 1, 0, and 1, 0, 0. So this is the corresponding matrix. So yeah, this is the corresponding matrix to 1. About 2, let me do that in the next page. And 2 is when n is equals to 4. And the element is given by 1 goes to 3, 2 goes to 1, 3 goes to 4, and 4 goes to 2. Okay, so let me write down the where this is being taken. So E1 goes to E3, E2 goes to E1, E3 goes to E4, and E4 goes to E2. So we should be able to write down the corresponding matrix here. So E1 goes to E3. That means the first column is going to be 0, 0, 1, 0. So 0, 0, 1, 0. E2 goes to E1. That means the second column is going to get the first element 1 and the rest is 0. E3 goes to E4. That means the third column will have 1 at the end and the rest is going to be 0. And E4 will be taken to E2. That means the fourth column will have 1 at the second entry and all the rest are zeros. Okay, so hopefully this provides at least some basic understanding of how the linear transformations and the matrices work when the bases are announced beforehand. If you recall from last time, I said that this is a natural way to identify the set of matrices of order n by m and the linear transformations from a dimension M space to a dimension N space. Only then it is natural or it is canonical whenever at the beginning you actually announce the basis. In both of these problems, really, we have announced the basis beforehand, and that is why this is a very natural way to identify these transformations and the matrices. Okay. So let me move on to a different kind of problem. The next two problems are going to be about the range and the kernel of a given linear transformation. Okay, so let me just start with finding the kernel. So how do you do that? Basically, remember what kernel means. Kernel of T is really the set of all elements X such that T of X is equal to 0. Okay. So in this case, what exactly do we have to do? We basically have to look at all the xy's such that x plus y is equals to 0, and so is x minus y. So basically, we have to solve a system of equation which is x plus y equals 0 and x minus y equals to 0. Now, what does that really mean? From the first one, we get that x is equals to, let me actually write it down. From the first one, we get this, which actually implies that x is equals to minus y. And from the second one, we get x minus y equals to 0, which is equivalent to saying that x is equals to y. And if this were to happen simultaneously, then this could imply that y is equals to minus y. By the way, when I say R2, I actually mean vector spaces over R. So this is a characteristic 0. Okay, this is a characteristic 0 case. So that means y is equals to 0. And since y equals to 0, from either this guy or this guy, you actually get that x is equals to 0 as well, which means in this case, the kernel is just this vector. And that means that T is injective. It is a monomorphism. Now remember, from the rank nullity theorem, that the dimension of the kernel plus the dimension of the image of T has to be equals to the dimension of this one, which is of course 2. Since kernel is it's just the 0 vector, it means that the dimension is 0, which means that the dimension of the image of T is 2, which actually means that this is surjective. Okay, you can use the rank nullity theorem here, or you can directly compute. You can just pick random elements A and B from R and try to see if this system has a solution or not. In fact, it will have a unique solution because it is, injective. And if you solve them, you will see that it must imply that x is a plus b over 2 and y is a minus b over 2. Okay, so that means for any such a and b, you will have a solution. You will have a unique solution in x and y. That means this is really an isomorphism. This T is really an isomorphism. So the range is the whole thing, and the kernel is trivial. Okay. Okay, let's do another problem like this, which is hopefully slightly different than the last one. Okay, so the same story here. We have to find the range and the kernel of the linear transformation T. Let's start with the kernel like we did last time. So we basically have to solve the system. X plus z is equals to 0. X plus y plus 2z equals to 0. And 2x plus y plus 3z is equals to 0. And okay, so what does that imply? Let's look at the first one. What can we really say from there? We can say that x is equals to minus z. Okay, from the second one, we can say that actually we can use the first one, that x is equals to minus z. We can use that equation. And from there, we can deduce that y is equals to minus z. Okay. And that is the relation that you want. If you just use this in here, you will see that this equation will be satisfied. Okay, so you are not getting any new information out of the third equation. So that actually gives you the kernel, that x is equals to y, and the last coordinate is the negative of the first two coordinates. So that's exactly what the kernel is. Kernel of T, it basically comprises of the vectors x minus x, but x is in R. Okay, and you can see clearly that the dimension of the kernel of T, which is really the nullity of T, is equals to 1, which implies from the rank nullity theorem that the range of the rank of T will be of dimension 2. Okay, and one thing we should notice here is that say the first row is R1, the second row is R2, and the third row is R3. Then R1 plus R2 is actually equals to R3, and that really gives you the range. Okay, so the image of T is going to be the set of all vectors A, B, A plus B, where A and B are in R, the set of real numbers. Okay, and you can indeed do some calculations and convince yourself that this actually works. Okay, and the calculation is going to be pretty basic. Let me see if I can copy this or not. So if you want to convince yourself that you are going to get all the elements or all the vectors of this type, you just have to solve for something like this. And it's pretty easy to see that if you take x to be equals to, let's say, A should work. And you can take z to be equals to 0. And then y you can take to be equals to b minus a. Okay, then you can see that all of these equations will be satisfied. So indeed, this is the image. And it cannot be bigger than that because this is dimension 2 and the image of T has dimension 2. All right. Any questions at this point? Okay, just want to check. Everyone can still hear me, right?
Yes.
Okay, thank you. All right. So let's see a slightly different flavored problems. This is basically two problems really. So can you construct a linear transformation T with this kind of image, where the sum of the entries is going to give you 0? Okay. So first, let's say that you can construct it. Okay. Let's say you can construct it and try to see this in terms of the rank nullity picture. Okay. So what would be the image or the dimension, rather the dimension of the image of T? You can see that x4 is dependent on x1, x2, and x3. So x4 is going to be determined by x1, x2, and x3 alone. So basically, this is dimension 3. So if let me actually number them, it would be easier that way. So let's call this one 1 and this one 2. So I'm talking about 1 now. So clearly, dimension of image of T is equals to 3. Now, if you try to use the rank nullity theorem, you will see that this is ridiculous, because this plus the dimension of the kernel must add up to 2. But you already know that the dimension of image of T is equals to 3, which you can only conclude from there that the dimension of the kernel of T has to be -1, which is impossible, right? The dimension cannot be negative. So you cannot really construct it. That is not possible. And you can see that how the rank nullity theorem actually helps you in order to see that how ridiculous this sounds. But 2, you can actually find it, okay? Because you see, for 2 also, you have similar kind of idea that all the entries add up to 0. And the dimension of the image of T, in that case, is 2. Which implies from the rank nullity theorem that the dimension of the kernel of T is equals to 0, because this is dimension 2, which means that T is injective. T has to be injective. If such a linear transformation is to exist, then T has to be injective. Now it's time to produce the transformation, because that is what we are trying to get to. And the image, the description of the image gives you the idea that what exactly do you want. You want to describe the image of T in such a way that the components add up to 0. So you do that. You define T x1, x2 equals to this dimension 2, so 2 entries only, equals to x1, comma x2, comma, so there is no space here. I should write minus x1 minus x2. That's the third entry. Okay, and you can see that it satisfies all the conditions, and it works. It is injective. Okay, so the first one we cannot construct, but the second one is very real. It actually exists. Okay, so let me move on to a true-false kind of question. You have two statements, P and Q. In P, you have a system of equations, AX equals to B, where A is a matrix of order m by n, and B is a column vector. And we are talking about the solution of the system, AX equals to B, and And if this solution is unique, then that must imply that m equals to n. So this is the statement, and we have to see if this is true or not. That is what the statement P is saying. About the statement Q, you have a subspace of a vector space V. It can be any vector space you want. It doesn't say it exactly. It doesn't make anything precise. Any vector space. You are picking any two elements from V, but in such a way that these two elements cannot be in W. Then U plus V must also be in V, but outside W. Is that really true? That's what we have determined. All right. So the answer is actually both are false. Let's give an example that why this is false. First, let's consider P, the statement P. Now, take A to be the matrix 2, 3, 0, 1, 2, 0, 1, 0, 0, and the last row comprises of only zeros. That's your A. And your B matrix, I think I use small letter b, yes. So B matrix is 5, 3, 1, 0. Okay, so let's look at the solution. So A, X equals B. So 2, 1, 1, 0, 3, 2, 0, 0, 0, 0, 0, 0. Okay, looks good. And then x1, x2, x3, and 5, 3, 1, 0. All right. So if we write it down as a system, we get 2x1 plus 3x2 is equals to 5. x1 plus 2x2 is equals to 3. And x1 is equals to 1. Okay, and then the last one doesn't give you anything, so I'm not writing anything. All right, so you have x1 equals to 1. If you plug that in the second equation, you get x2 is also equals to 1. And okay, one sec there. Yeah, there is one entry seems to be missing. Let me see what can be done. Yeah, sorry about that. This I think is 1. So 0, 1. Okay. Okay. So now it's all good. So now x2 is equals to 1. And from the first two, you can actually see that since these are linearly independent equations, that the coefficients are not proportional. So you will have two distinct lines, and they will intersect. These are non-parallel lines. This will intersect, and it will produce a unique solution. Okay, so P is definitely wrong because m is not equals to n. In this case, your m is equals to 4. You have 4 rows, and n is equals to 3. All right. So that's the story with P. What about Q? Actually, Q requires much smaller argument. say, in fact, I can even write Q here. So Q, say you take in any vector you want, U, and the V you take as minus U, okay? But since it's a vector space, if U is there, then minus U must also be there. And similarly, if U is in V, but outside of W, then so is minus U. So this satisfies this criterion. And then if you add them up, you get 0, which obviously is in W because it's a vector subspace, and every subspace has the 0 element. Okay, so this is true. Both of them are false. Okay. Now this problem is okay. Or some of the other problems that I've that we have seen before was taken from previous GATE examinations, and this one was also from GATE examination, but it seems to be very popular in the competitive exams. So I think it would be a good choice on our part to look at the idea of how one can do this. And in fact, it took me a little time because I've not seen this problem before. It took me some time to figure it out. But the idea is the dimension is 1. And I was playing around with how many linearly independent matrices I can actually take. And it turns out that even 2 is failing. So the only possibility is 1. So that's how I determined the dimension. And by this problem, you can actually see that how rare these invertible matrices are, because this M7C, this vector space, is of dimension 49. And I'm claiming that the dimension of V, which is the set, which is the subspace of all, which is the subspace which contains every invertible matrices and maybe some more with all linear combinations, is dimension 1. So there might be some more matrices in there. If you throw in more matrices, and you still get so much less dimension. So the invertible matrices are quite rare, if you think about it that way. Anyway, so let's get on to the argument. And this is a problem which is a theoretical problem, not actually with numbers problem. So let's do it. So as I said, I was playing around with the 2 matrices, which I'm claiming to be non-zero and distinct. So let A and B be matrices in V such that they are non-zero. A and B are non-zero and distinct. Okay, and that means by the hypothesis, A and B are both invertible. Every non-zero matrix in V is invertible, so A and B are both invertible. So in other words, in particular, we can actually say that A inverse B, this is a matrix of order 7. This is an invertible matrix. Okay, so this is an invertible matrix. Okay, that's good. Since this is invertible, all the eigenvalues that A inverse B has must be non-zero. Recall from last time that a matrix is singular if and only if 0 is one of the eigenvalues. So this is invertible. That means 0 cannot be an eigenvalue. That means there exists some delta eigenvalue which is not equals to 0 and some eigenvector x, and since it's an eigenvector, there's also a non-zero matrix I mean a non-zero vector, my mistake, non-zero vector such that A inverse B minus lambda of the identity matrix. In this case, the identity matrix is, 7 of order 7 times x must be equals to 0. Okay. I'm multiplying both sides of this equation by A. That gives me B minus lambda A x is equals to 0. But see, x is a non-zero vector, and B minus lambda A is a vector which is a linear combination of B and A. So from here, I can actually say that that the determinant of B minus lambda A is equals to 0, because some linear combination of the rows is basically giving you 0. In other words, the rows are linearly dependent. That means B minus lambda A is singular. Which means that B and A are not linearly independent. Okay, so this means A and B are linearly dependent. So what we have done is we have taken two arbitrary matrices which are both non-zero and which are distinct, and we have shown that they are linearly independent. That means there cannot be any set in V having more than one element which is linearly independent. That means the basis has to have only one element, and that means the dimension can be 1, and this is the only possibility, because recall from last time that the basis is nothing but the maximal linearly independent set, and since there cannot be more than there cannot be a linearly independent set having more than one element, the dimension has to be equals to 1. Okay, so this I personally believe is a very nice problem. So hopefully you have enjoyed it. All right. So the next problem is about polynomials over R in one variable, such that the degree of the polynomials are at most 12. If we have actually seen this kind of example last time, it might not have been exactly that, but very similar. And we have shown that the dimension of such a vector space over R, of course, is 3. Dimension 13. I mean 13, because this is 12. Okay. So this is dimension 13. So we have to determine the dimension of V, where V is expressed in this way. Now we have to think about this. First condition is looking at this guy. Fx equals f of minus x, which means f is an even function. For polynomials, what even function means is that you cannot have any monomial in the polynomial which has odd degree. So this is the same thing as saying in terms of polynomial only. This is not true in general, of course. For polynomials, it means that fx is really a polynomial that looks like a g of x squared. Okay, so to be more precise, fx looks like some, say, a0 plus a1 or maybe a2x squared. Let's keep track of the indices that way: a2x squared, a4 x to the 4, and so on up to a12 x to the 12. So when I say so on, I mean a6 x to the 6, a8 x to the 8, and so on. That way, only considering the even powers. So if that was the only description of V, then we would have said that the dimension of V has to be the cardinality of this set, which would have acted as the basis if the other condition was not there. The basis would have been, 1 x squared x to the 4 up to x to the 12, which contains 7 elements. So the basis would have been 7. But here, this extra condition is provided. So that will reduce the dimension. What exactly is this saying? It's just saying that 2024 is the root of every polynomial in V. Okay, if 2024 is the root, then because of this condition that you have, minus 2024 is also a root. So in other words, that means for every polynomial in V, so for all f in V, one has the fact that x squared minus 2024 squared, whatever that is, must divide f. So this condition actually reduces the possible basis. So you really don't have to consider up to x to the 12. You have to consider up to x to the 10, because x squared minus 2024 squared is already a factor. So what else is there has to be a polynomial that looks like a0, a2, x squared up to a 10, x to the 10. So you can actually compare it to the vector space, which has as a basis 1, x squared, x to the 4 up to x to the 10. That means the dimension of V is equals to 6. Okay. So this is another nice problem, I think. You have a vector subspace of the vector space M7R, which is defined in this way, that all the matrices that it contains is comprised of these blocks. T and S are blocks really, and 0 and 0s are also blocks. So T is a 3 by 3 matrix and S is a 5 by 5 matrix. So in other words, wait, this is 8, not 7. Yeah, sorry. M8R. So the T is a 3 by 3 matrix and S is a 5 by 5 matrix. And there's more. The transpose of T must be equals to minus of T, and the trace of S must be equals to 0. By the way, when I say trace of S, it actually means that the sum of the principal diagonal is equals to 0. Okay, so all we have to do, so it's easy to actually determine the dimension of V, because the dimension of V is governed by the sum of the dimension of T. So this is a very bad way to represent it, but when I say T, I mean all the possible T's, the subspace of all the possible T's that satisfy this. So I don't mean the matrix T, I mean all such possible matrices. And then the dimension of S. Again, by S, I mean the subspace of S's such that the trace of S equals to 0, which is pretty easy to see. Okay, so what is the dimension of T? So let's just think about this condition, that transpose of T is equals to minus of T. Let's write down the transpose of T. Say T is equals to A, B, C, D, E, F, and G, H, I. Then transpose of T is equals to A, D, G, B, E, H, and C, F, I. by hypothesis, this is supposed to be equals to minus of t. That means this is supposed to be minus of A, minus of B, minus of C, minus of D, minus of E, minus of F, minus of G, minus of H, minus of I. Now you compare these two guys, these two matrices, and you can, by the way, this is also a vector space over R. So in particular, this is characteristic 0. So A equals to minus A actually means that A is equals to 0. So A is equals to 0. So is E, and so is I. These are the diagonal entries, principal diagonal entries.
Sir, can we directly say that the condition given T transpose equal to minus T is a skew symmetric matrix? Set of all skew symmetric matrices?
Skew symmetric matrix.
Can we directly
Actually,
we
yes,
directly
please.
say that?
Yeah, you can say that. That's what I'm trying to say.
Yeah.
Actually, yes, you're right.
Okay.
This is skew symmetric matrix. Yes, you're right. So this is skew symmetric matrix, and that means B is equals to minus T, C equals to minus G, and F is equals to minus H. Okay, so that means basically your T's must look like 0, 0, 0, B minus B, C minus C, and F minus F. So all you have to do is determine B, C, and F, and all the other entries is already known. So the dimension of, again, this T thing, let me actually write it in quotes so that you guys don't get confused. So not 0, I meant 3. I should write it in quotes. This is not really T. It's a very bad way to represent it, but anyway. So this is dimension this is dimension 3, and for the trace of 0, that only gives you a condition on the principal diagonal, and it says nothing about the other entries. Okay, so if your S matrix is written as A11, A12, up to A15, and similarly A51, A52 up to A55, then what trace of 0 is saying, what trace of S equals to 0 is saying, is that A of 55 is equals to minus of A11 plus A12, not A12, A22 plus A33 plus A44. Okay, so A55 is determined by these 4 guys, and the rest we don't know. So we actually have to pick these things. That means the dimension of this S thing is only 1 less than the total dimension, which is so the total dimension was 25. That means this is 24. 25 because it's a 5 by 5 set of 5 by 5 matrices. So 25, and here is you get 24. So you add them up, you get the dimension of V is equals to 27. Okay. All right. So let's look at this problem. This is also interesting. Say I give you a vector space V over any field. Actually, you know what? Let's take R to be the field. Okay, let's be precise. Let's R be the field, and T be a linear operator. So linear operator just means that the domain and the codomain spaces are the same space. Okay, that's when we use the phrase operator. So T is a linear operator on V, such that the image actually is equals to kernel of T. that actually makes sense. This equality actually makes sense because we are comparing two sets inside the same vector space. So equality actually makes sense. Then prove that n is an even positive integer. Well, that's actually easier than you think because it follows directly from the rank nullity theorem. Because dimension of V is equals to n, we must have n is equals to the dimension of kernel of T plus dimension of image of T. But kernel and the image are the same. So these are really 2 times something. 2 times, let's say, dimension of the kernel of T. You can also write the other one, doesn't matter. Which means that 2 divides n, which means n is even. Okay, so this is a pretty interesting problem. It's very short, but it's interesting. Let's look at other problems which involves this image and kernels. And so some relations where the intersections actually give you 0. We have 2 problems like that, which are the following 2 problems. Say you have a vector space V, a linear operator on V, and you have 2 statements which is about some conditions on T. The first condition is saying that the image and the kernel, the intersection is trivial. Trivial meaning the intersection is 0, the least possible intersection. And the second statement is saying that if alpha is such an element of V such that T of alpha is equals to 0, then that actually means that T of alpha is equals to 0. In other words, that actually means that alpha is in the kernel of T. We have to show that these 2 statements are equivalent. Okay? So let's see how one can show that. Let's try to show that 1 implies 2 first. So I want to show that if alpha is such an element with satisfying this condition, then we must have this. That's what we want to show. So pick one alpha such that T of alpha is equals to 0. So T of alpha is equals to 0. But what does that really mean? That means T of alpha is in the kernel of T, since T of alpha is equals to 0. But T of alpha is also in the image because this is an image of alpha under T. And the given condition says that this is equals to 0. That means, T of alpha is equals to 0. Okay, so that proves one direction. What about from 2 to 1? So given that T of alpha equals to 0 implies T of alpha equals to 0, we have to show that the intersection of the image and the kernel is trivial. So the other direction, 2 implies 1. So say I pick an element from image of T, intersection kernel of T. I want to show that X must be equals to 0. Okay, so if X is in the kernel of T, that means what? That means Tx is equals to 0. But X is also in the image of T. That means there exists some Y in V such that Ty must be equals to X. Okay, for some Y in V. These 2 together imply that T of Y is equals to 0. Right? All I'm doing is that replacing X by T of Y. Okay, and now 2 was saying that if this thing were to happen, then that must imply that t of y equals to 0, right? But by hypothesis, this is equals to x. So we get x equals to 0. That means that the intersection is trivial. Okay. Any question at this point?
No, sir.
Okay, so this is, you can see the also image of t intersection kernel of t is 0. That we have to prove that. Well, I want to use this equivalence that we have just proven. Okay, and using that equivalence, things become the number of steps is required to prove this is lesser. Okay, just because we have problem 12, problem 11, and we have proven the details. All right, so we start with a finite dimensional vector space. I'm not saying what the dimension is. It's any finite dimension. T is the linear operator on V. And suppose that the rank of T is equals to the rank of T squared. Now, if rank of T is equals to rank of T squared, okay, maybe I should actually write down some detail at least. See, T is a linear operator. That means that T squared is also a linear operator on V. So we have this, that that dimension of V is rank of T plus nullity of T. I'm writing nullity as null of T. Okay, but from using the same rank nullity theorem, but T squared instead of T, we have that rank of T squared plus nullity of T squared is equal to dimension of V. By hypothesis, these two guys are equal. That means these two guys must also be equal, because the sum has to be the same, right? So that is the only possibility. So we conclude that nullity of T must be equals to nullity of T squared, which implies that kernel, since this is finite dimensional, this implies that kernel of T is equals to kernel of T squared. And you see what does that mean? That actually means that if we have T of alpha, that actually will give you T of alpha equals to 0, right? Because T squared, because kernel of T squared is the same thing as kernel of T. Okay, and since these two statements are equivalent, that means the image of T must be equals to the kernel. Sorry, the image of T intersection kernel of T must be equals to 0. Okay, so let me just write down, the rest follows. From the previous problem. All right. So we have two more problems. This is the second last one. Say T is a linear operator on R3 that is described in this way: x1, x2, x3 is being taken to a vector where the first component is 3x1, the second component is x1 minus x2, and the third component is 2x1 plus x2 plus x3. We have to, these are two problems really. First, we have to determine if T is invertible or not. In other words, we can use the standard basis of R3, which we have already described in problem 1, I think, or might have been problem 2. I don't remember exactly. 1, 0, 0, 0, 1, 0, and 0, 0, 1. We can just start with that standard basis, and we can look at the corresponding matrix of T. Let's call it A, for example. And if A is non-singular, then T is going to be invertible. And if A is singular, then T is not invertible. And say if we show that the corresponding matrix is non-singular, then T inverse will be described by the inverse of the corresponding matrix A. Okay. So let's do that. So what is the corresponding matrix? I'm using the E1, E2, and E3 like we did in problem 2, I think. So let me actually write it down. So E1 is 1, 0, 0. E2 is 0, 1, 0. And E3 is 0, 0, 1. So what is T of E1? T of E1 is, you can calculate that, 3, 1, 2. You know, where x1 is 1 and the other two are 0. So 3, 1, 2 is what you are getting. T E2 is 0, minus 1, 1. And T E3 is 0, 0, 1. Convince yourselves that these are the right numbers. Okay, so where is it? I want to represent this in terms of the same basis on the codomain. So I can write this as 3 times E1 plus 2 times one times E2 plus 2 times E3. This is 0 times E1 minus 1 times E2 plus 1 times E3. This is 0 times E1 plus 0 times E2 plus 1 times E3. So what is the corresponding matrix? Let me try to squeeze it in here. Let's call it A. Then it's going to be 3, 1, 2, 0, minus 1, 1, and 0, 0, 1. Okay. Yeah, looks good. And you can calculate the determinant. This is a non-singular matrix. You can check. And that means that T is invertible. Okay. All right, so the first part is done. And the A inverse, you know how to calculate the inverse of matrices. So A inverse, let me actually use the next page. We have space. Let me copy the matrix from here. So you can calculate the A inverse. Not that bad. 1 over 3, 1 over 3, minus 1, 0, 0, minus 1, 0, 1, 1. Okay. Now T inverse is going to be given that way. Sorry, we were using x1, x2, x3, so let's stick with that. x1, x2, x3. Is going to be 1 over 3 x1 plus 1 over 3 x2 minus x3. The second entry is going to be minus x2 plus x3. And the third component is going to be x3. So that is the T inverse, where of course the components are chosen. So this goes with this goes with this, and similarly this goes with this. Okay, and that's all we wanted from this problem. The last problem is quite nice actually. You think about it. It talks about one linear transformation which goes from R3 to R2, and another linear transformation which goes from R2 to R3. Then you have to prove that U compose T is not invertible. Okay, it is easy, but you have to just look at some finer details that this kind of problems provide. This R3, since you are going from a higher dimension to the lower dimension, you cannot have an injective transformation. So T cannot be injective really. Why? It's simple. The argument is simple. I mean, say this is R3, right? So I'm going to use the basis E1, E2, and E3 of R3. So E1, E2, E3 is a basis of R3. So in particular, E1, E2, E3 is a linearly independent set. But what can we say about this set? TE1, TE2, TE3. Well, T is going to R2, which has dimension 2. If this is dimension 2, the codomain is dimension 2, then you cannot have a set which is linearly independent and contains three elements, right? So this must be linearly dependent in R2. Okay, that means T is taking a linearly independent set to a linearly dependent set. That means T is not injective. Okay. Since TE1, TE2, and TE3 are linearly dependent, that means there must be, so this implies that there exists some constants, not all zero, such that summation of Ci, Ei is equal to 0. When I say summation Ei, I mean C1, E1 plus C2, E2 plus C3, E3. I'm not using the dots here, right? Because this is linear. Sorry, I missed the T.
Sir, all EIs are.
Yeah, go ahead.
No.
So I didn't understand the question. Can you repeat that?
Oh, we have previously write that C1 summation of CIEI equal to 0 for all not CIs are 0. So this proves that EIs are not linearly independent. But you correct this one.
Yeah. So yeah, that was a typo. I wanted to write T of EI, not EI. Okay. So I've rectified that. Summation CI times T of EI is equals to 0 because T of E1, T of E2, T of E3 is a linearly dependent subset of R2. Okay. Now, what does that mean? That means that since this is a linear transformation, T is a linear transformation, I can actually get everything inside. I can write the summation Ci Ei is equal to 0. Okay, which means that I'm applying U on both sides. U compose T of summation Ci Ei is equals to U of 0, but this is a linear transformation, which means this is 0. What that implies is kernel summation of Ci Ei is in the kernel of U compose T. Right? But you see that this guy right here, so C1 E1 plus C2 E2 plus C3 E3 is not equals to 0. We have chosen it that way because if this were equal to 0, E1, E2, E3 being a basis, that would imply that C1 is equals to C2 is equals to C3 equals to 0. And we have already chosen C1, C2, and C3 in such a way that not all of them are 0. So this guy cannot be equal to 0, which means that U compose T is not injective because there is a non-zero element in the kernel of U compose of T. And that's all we wanted to prove. Now there is another part though, which says that can this be generalized? Well, yes, this can be generalized because of the argument that I said. All you have to do is go from a higher dimension space to a lower dimension space. So the one possible generalization would be in this way. That let M and N be natural numbers such that M is greater than N and T is a matrix, T is a linear transformation that goes from Rm to Rn. And U goes from Rn to Rm. Then U compose T, which is really from, let's see, Rm to Rm is not invertible. In fact, it's not injective. The injectivity itself fails. By the way, the problem was about invertibles, yes, but we have shown that this is not injective, so obviously it is not invertible. And the proof is exactly the same. Instead of starting with 3 elements, you start with m elements and continue with the same logic. Okay, that exactly the same arguments work.
Okay, thank you, Sayak, for this nice session. Today, you have did a lot of problems, which are very nice problems. So, okay, dear participants, now it is your time. Please do share the feedback, or if you have any queries, you can ask it.
So, my name is Kirtana and I'm studying in PhD College of Arts and Science, Coimbatore. So, actually, around 3 months ago, I had participated in a program called MTPS.
Sir, am I audible?
So, I think that was when I really started learning linear algebra. And after that, I haven't really learned it much because our sir has been focusing more on real analysis. So for me personally, the class taken today, the questions we had today, it felt easy enough for me personally to understand. At the same time, it felt like I was learning something very new. And the way you explained each problem, each point, it was well put, I would say. So personally for me, it was very useful because I got a chance to revise what I learned as well as learn a lot of new points. Thank you a lot.
Thank you.
Okay, thank you, Kirtana.
Good evening, sir, to both of you. And Saik, sir, this is my second session with you. First session was about linear algebra, and this is about linear transformation. The one thing that I want to mention was the thing that I like the most is your approach towards the problem. The thing is, everybody can solve the problem. I have attended other classes. I have gone to coaching centers. Their approach and your approach towards the problem was entirely different, and it was very it is very simple and to the point. It was core to the point, and thanks a lot for the valuable insights that you have given on the subject, sir. And once again, I thank Vinod sir for arranging one such sessions, and we are looking forward for these kind of sessions in future, sir. Thank you so much.
Thank you.
Okay, thank you, Revati.
Uh,
Yeah,
Excuse me, sir.
yeah.
Yeah, so I just wanted to say something on a problem where we were in R3 and linear transformation was given explicitly like 3x1 comma x2 minus x1 comma 2x1 in that format, and we were asked to find if t is invertible and also give the inverse explicitly. Now, one idea will be to write it in the standard basis to give a matrix representation for T and then check if the matrix is invertible and find the inverse and get back from find the T inverse and then get back the explicit form from that. And the another, since we are working in R3 and only 3 variables, we can think of it as a system of linear equations. And giving an inverse means to get back the original variables from the from the result. So we could it just means if we can get a consistent if it is a consistent system and we have one solution, so we will either we can use the matrix method to find the rank, and then if the rank is equal to 3, then we say it's invertible and all, and if not, we can just since it's just 3 variables, we can try to sort of find the original variables from the new variable, like take the result as x1 dash, x2 dash, and x3 dash, and then find the inverse. And if that is like if that is possible, like if it can be done linear independently, like every step you can find the solution, then yeah, so I was thinking in that way, so I just wanted to know if that's right.
Yeah, that's right. That's perfectly correct. So you just have to find the kernel first, and you have to show that the kernel consists of only one element. That proves the injectivity part. And then the second part, the onto part, is what you talked about. It is consistent. You will get a unique solution of ax equals to 0. And yeah, that works. Yes.
Okay, thank you.
Okay, Madhuvanti, could you introduce yourself?
Yes, sir. I'm Madhuvanti. I'm MSc graduate. I have completed my MSc. Currently preparing for entrance exams.
Okay, you are from?
Thank you.
I'm from Tamil Nadu. I have done it in Pondicherry University. My MSc.
Okay, thank you.
Okay.
Thank you.
One other thing that I would like to say, Madhuvanti, is that in there, it was going from R3 to R3. And if you remember from last time, if the if the dimension is the same, dimension of the domain and the codomain is the same, then injectivity implies surjectivity and vice versa. So in this case, you just have to show the injectivity. You don't even really have to look at the onto part. Just the injectivity is good. Okay.
Okay, sir. Thank you.
Okay, thank you, Madhuvanti.
Sir, I have a questions.
Okay.
Sir, hello, sir. Namaste to both of you.
Yeah, good evening, sir. First of all, thank you, Sayak sir, for this wonderful session. It was really nice because the notes were really like easy to understand and it was very simple and precise. Even the questions, yeah, I'm kind of getting better in linear algebra. So when I read the questions, yeah, I get some idea, but I didn't know these questions were this easy. So like the solutions you made and the way you explained was really good. And thank you for this. I'm pretty sure that this will be useful for all of us.
Thank you.
Thank you, Isha.
I'm Disha from St. Thomas College, Kerala. Thank you, Sayak sir, for this wonderful section. And this section was too helpful for us to do more problems on linear transformation. And thank you.
Thank you.
Okay, thank you, Drishya. Miss Nandana.
I'm audible.
Yes.
Yeah.
I'm Nandana came from St. Thomas College, Thrissur, Kerala. Thank you, Sayak sir, for this great session. And the class was very effective as you discussed many important problems. And I also like to thank Vinod sir for conducting this session for us. Thank you, sir.
Thank you.
Thank you, Nandana. Others?
Good evening, sir.
Yeah,
Good
yes.
evening.
Yeah. Yes,
I'm
Vanadi.
Vanati from PGR Krishnamurti College, sir. And this session was wonderful and thank you for this great session. And at first I felt very tough in algebra, but now I'm able to connect with the problems which sir taught. So this problem gave me an idea to solve further problems. And thank you, wonderful. Thank you for this wonderful session, sir.
Thank you.
Thank you, Vanadi.
Hello, sir.
Yeah.
Hello.
I am Lakshmi. I am from PMC College, Tirur, Kerala. Thank you, sir, for this wonderful session. You explained each and every question clearly, and it was really helpful. And once again, thank you, sir, for spending your valuable time with us. And thank you, Vinod, sir, for organizing this session. Thank you.
Thank you.
Yes. Any others? Yes, Varada.
Sir, am I audible?
Yeah, sure.
Yes.
Good evening, sir.
Good
So
evening.
about today's session, I felt the session was really productive as well as engaging. I mean, like you explained all the concepts of linear transformations like in a very detailed manner. So like it was really helpful to understand. And yeah, so thank you so much, sir, for putting so much efforts in making us understand as well. And thank you, Vinod, sir, for organizing such a great opportunity for us.
Thank you.
Thank you, Varada. Any other, if any of you would like to share a feedback, you can do it now. Otherwise, we will wind up the session now. Okay, thank you, Dr. Sayak, for today's session was very interesting because you have collected a lot of good problems from linear transformations. I have seen that many questions are taken from the exercise part of Hoffman. All that are very nice questions. So I'm sure that those who have seriously attended the session will be really got benefited out of today's session. Okay, thank you, Sayak, once again. And also I request you to be with us to handle more such sessions in our platform.
Thank you.
Thank you. Let us wind up.
Yeah. Have a good night.
Yep.